Hello, my name is Bob Wadja, and I'm the Applications Manager at Kayaku Advanced Materials. I'm presenting on our accepted paper for the 2020 Compound Semiconductor Manufacturing Technology Conference that was to be held the week of May 18th. This presentation is a summary of the more detailed paper, which is available upon email request. My email address is shown here and again at the end of the presentation. So Kayaku Advanced Materials is a division within the Functional Chemicals Business Unit of Nippon Kayaku Group out of Tokyo, Japan. We are located outside of Boston, and at our facility, we have the capability for complete R&D through manufacturing of products. We offer a range of technologies in terms of permanent photo patentable epoxies, all the way to liftoff resists and other ancillary products. The work being presented on here concerns our PMGI LOR liftoff products, which are typically used in bilayer processes for liftoff of metallizations and other films. So the project was initially motivated by the benefits demonstrated in prior research, showing that VCSEL fabrication had the potential to be simplified and cost reduced by using self-alignment methods. And I've referenced a seminal publication on that technology at the bottom of the slide. Basically, in addition to that, given the market drivers and performance benefits of the 5G rollout, there's almost endless applications, it seems now, where this type of technology can apply. Since time to scale up advantage is very huge in the electronics industry, it seems logical to effectively extend the materials that are available for new products if possible. And the basis of this work really is born out of Stoney's formula, which describes the characteristics of a cantilever beam under stress. It's a very convenient model to apply to a bilayer structure owing to its characteristics. And as you can see here, the image to the left depicts a typical bilayer structure that's used in liftoff. You can associate the various structure variables such as resist thickness, undercut, and whatnot to specific variables in Stoney's formula, which you can see that I've provided off to the right. So basically, the deposition process and film material become the stress affecting the cantilever beam. The resist materials, as well as geometric dimensions selected, which are mostly adjustable in the case of a bilayer liftoff type design, which is something that's unique, can essentially guide you to a usable set of guideline design aspects for the structure being used for a given process and material set. And what's mostly novel about the work that we're presenting here is that aside from looking at sputtering, it's addressing insulator films. The conformal coatings are not normally the domain of a liftoff process because of their conformal nature, but in the case of a bilayer design, you can take into account for certain aspects of that type of deposition and material. Generally, bilayers are probably most popularly known for use with metallization schemes and more commonly evaporation type technologies. So the first step towards understanding how an insulator deposited by sputtering might be different from an evaporative metal process is to recognize the directional characteristics and ion bombardment effects. They're not the same for both types of processes. And as you can see from basically the early structure that was fabricated, we have a condition that looks very stable, and under an evaporative metal deposit would work quite fine. However, in the case of a sputter deposition, where you have a lot more ion bombardment, you can see that simply, 1500 angstrom deposits of silicon dioxide cause a significant amount of deflection of the beam, or the top side resist on the bilayer structure. So initially we had to sort of go about quantifying what the interactive variables were, which seemed more or less sensitive at different deposition thickness points, and effectively looking at the outputs from multiple runs to understand how interactive these were and how to optimize them as a combination. And so, as you can see here, the approach was to effectively categorize the structures depending upon the amount of deflection of the beam, and whether it was uniformly deflected. In the case of something with significant deflection or irregularity in the symmetry of the structure, it was just considered an unstable outright reject. If it was bowed significantly, it was considered a reject. If there was a very, very small deflection and it didn't appear that it was having any effects on the uniformity of the deposit, we would consider something like that borderline accept. But for the most part, what we were really looking for was undetectable change in the symmetry or flatness, essentially, of the top layer resist relative to the substrate. And for the deposition ranges that we initially looked at, which was about 1,000 to 2,500 angstroms, looking at 6 micron to 9 micron lines and spacings, we were able to get pretty stable structures with a range of about 2 to 3.6 micron top resist thicknesses, with undercut ranges of 1.8 to 2.5 microns. The pedestal is a critical element in the stability of the structure, and our findings indicated that down to just below about 1 micron, we were able to get high stability geometry. The other element of basically an effective bilayer liftoff process is the liftoff itself. I mean, this is a major determinant in whether the masking structure is working, and it's essentially measured by how cleanly the sacrificial resist comes off, the uniformity of the deposit, the absence of defects like fencing or wings, which are related to the deposit material bridging or overspill into the undercut. We used basically a few approaches to assess that condition. One was basically a microscope and SEM visual inspection, as well as an EDS line scan analysis, looking for the presence of an oxide up onto the LOR sidewall. So that's the type of analysis that we were depicting over here with the images to the right. You can see one image essentially at the top is a picture of the lifted off area. You can see that the deposit edges are sharp, well defined. The resist has come off nice and complete and clean. And the EDS scan for that essentially shows good correlation, and no deposit of material up to the wall. So from assessing the structure stability geometry and the liftoff results, what's become apparent was this relationship between the top layer resist thickness and the deposit thickness. And that effectively helps to describe the cantilever condition from a stability standpoint. When you look at the ratio of the top layer resist to the deposit thickness, and you plotted that versus undercut, it revealed some very interesting correlations, largely a window of processing acceptability to get good liftoff and also essentially a stable structure. So here's what that relationship looks like graphically. For silicon dioxide, if you plot this resist to deposit ratio versus undercut, what you can see is that the blue dot points represent unstable structures or significantly bowing structures. Structures that were effectively deflected, perhaps borderline, are depicted with the black squares. And structures that were both structurally sound and had excellent liftoff were all depicted in the green triangles. Now, obviously, there are other factors that come into play in determining an optimal design. There's known collimation effects that occur with a thicker top resist layer, but our findings were that there was somewhat of an asymptotic relationship with that around 3 microns thickness for the top layer resist, where the benefit of going thicker didn't really have as significant a benefit as going, say, from 2 to 3 microns in thickness. So, in summary, these relationships yielded this predictive window for kind of setting up a process in context of what the bilayer structure needed to look like relative to the deposit thickness to get good outcomes. Next, we basically looked at aluminum oxide, and essentially we found very, very much the same results as we did with the silicon dioxide, but they seem to be offset by a factor. And it's believed that offset is related to the deposition properties of the particular material. We did also find that the thicker top resist here, more collimation of effect, seemed to basically be beneficial, more so than with the case of the silicon dioxide. That's likely related to the throw or momentum properties of the molecules under deposition. So practically speaking, for any given masking system, there's a cost process time benefit of being able to use the minimum top layer resist thickness to obtain the desired result. Also for LOR and PMGI materials, they're basically recognized for much higher temperature stability than most imaging top layer resists. Typically, they can go up into the range of 200 degrees C. So Kayaku Advanced Materials, we looked at this as a problem where we thought we could expand the capabilities of the bilayer if we were able to raise the top layer resist temperature. And as you can see, we did stress tests on these structures, and they were stable up to and exceeding 170 degrees C. So for reactive chemistry depositions like nitride or oxide depositions by low temperature PECVD, this may open up some potential windows for use of masking structures that may not have been accessible before. Some single layer resist systems, they just seemed to not work quite as well at accelerated temperatures, like the 150 degrees C deposition here of tin nitride. You can see how that material shifted in its stability prior to and then after deposit of the material. And in comparing that to the images shown above, with both basically a 2.3 micron top layer of high temperature resist and a 1.5 micron layer, both show very good stability for depositing a similar type of material. Likewise, we looked at basically the performance of the top layer resist changing to the high temperature version and compared that to the lower temperature SPR resist that the model had suggested, and we found that there was still continued good correlation, suggesting that this RD ratio undercut is largely influenced by the deposition type as well as the material. So basically, the model shows good performance to 5 micron lines and spacing capability. It offers unique geometry adjustability, and overall works well with conformal processes or reactive type chemistries. So, in summary, we have identified a process window model that aids in predictive requirements for working with bilayer structures and insulator materials. We've developed a new top layer resist that should, with the process window model described, further expand the possible application range for a bilayer masking structure. And finally, these findings are likely to enable support of new 5G sensor development and devices. And with that, I would like to thank you for your time and interest for listening to this overview presentation of our investigation. If you'd like to obtain a copy of the more detailed paper or have questions, please feel free to contact me. My contact information will display again on the next slide. And okay, then I'll leave this up for a bit and then close the presentation. Again, thank you very much. I appreciate your time and interest.